Now regarding the form 61, the diffusion, which is inside the cell itself, the aspect ratio, which is however is going to be the shape of the cell. The cell can be pyramid shape, can be, or if it is 2D, can be triangle shape or square shape, etc. So in general, the radius, or from the center of the cell till the largest or the farthest edge, A, divided by the minimum thickness, should be less than 5. This is why you're constructing a cell. If you find something like this, you need to refine the cells, make cell sizing, adaptation, etc. Cell skewness. It is also a relation between a cell and cell. If you find a cell and the other cell which is adjacent to it, it should be not more than or not less than 0.85. So if you find something which is increasing very big, you need to resize or refine this, the mesh, etc. Okay. Regarding smooth and smoothness and turbulence intensity. This is very important. This is just techniques above, and this one is very important, and it will continue with us later on. So what is a turbulence intensity? Turbulence intensity, it is how much RMS velocity divided by the mean velocity. RMS velocity is the peak velocity divided by square root of 2. Turbulence intensity, it can be generally written as a correlation of 0.16 Reynolds number for the hydraulic diameter power to 1 over 8 by minus. If it is 1%, it is very low turbulent. If it is 10% or higher, it is very high turbulence. Okay. Turbulence length scale and hydraulic diameter. Turbulence length scale and hydraulic diameter. First, we need to define what is the large eddy size. If you have a very big eddy, what is its size? Its size equal to 0.07 L, and L is the hydraulic diameter. Okay, so what we'll do, okay, in case of fully developed flow, we need to choose the intensity and hydraulic diameter method, intensity and the hydraulic diameter method, to define what? To define L, which is turbulence length scale, and the intensity. Okay, if I have a downstream turbulence due to vents, perforated plates, etc., downstreams, okay, what should yes, you still should need to use intensity method. This is I, you can calculate it, and this is hydraulic diameter, you can calculate it. Okay, but take care that L, which is in this one, it is calculated based on if this is the vein and this is the vein, and the flow is like this, so the entire volume is V, and this cross-section inlet area is A. L equal V over A. Okay, if I have a very big turbulence boundary layer, which is like in any cases, for example, airfoil, airplane, etc., whatever, so we need to remember our session regarding the boundary layer thickness. We need to calculate it, the boundary layer thickness, then it is 0.4 multiplies the boundary layer thickness, and this is L. L, not full L, not the big L, the L itself, the large eddy size. Okay. Okay. Now we'll need to go to this one, but first I will go to the turbulence viscosity ratio, etc., and all. Then I will go to this one. Okay. Turbulence viscosity ratio. It is what is the turbulence viscosity divided by the the viscosity for the moleculars, which is the normal velocity, which is we know it. Okay, so because the viscosity may change due to the turbulence, and it should be between the ratio between 1 and over than 1, and 1 it means equal no turbulence, and less than 10. Okay, this we need to consider it in free stream boundaries of external flow. So this condition needed to be valid. If it is not valid, your CFD work is incorrect. Okay. Just a check figure for you. Okay, the turbulence viscosity ratio. Okay, turbulence kinetic energy. It is internally calculated in the CFD, which is K. K, it is equal to 3 over 2 velocity average multiplied by turbulence intensity I. We already defined it before here. Okay, the CFD will work it for you, but square. But this is to understand it. Okay. Turbulent dissipation ratio. Turbulent dissipation ratio. It is an empirical relationship, but it is Cu 3 power 3 over 4 K. We already K. We know how to calculate it. Over 3 over 2 over L. L we know it. Large eddy size. Okay. So we can calculate what is the dissipation rate. Okay. Of course, you can break it down like rho Cu K square over mu multiplied by mu T over mu over minus 1. How I calculate it like this? It is just I'm breaking down uh, with an effect of the viscosity. Okay, everything we're going to know it. We know this one is a ratio of this one. We know this one. We can calculate this one from here. And rho, we know it. Cu, it is an empirical constant. In turbulence model, it's approximately 0.09. Okay. Roughness height and roughness constant. Ks and Cs. Okay. In some textbook, you will find Ks with M. Okay. Uh, Ks, it is equal 0, which is mean. The roughness height, which is mean, is very smooth. Roughness height, it is the height of the grains on the surface. Okay. If it is 0, this means very smooth, mirror. Okay. And if Cs equal 0.5, usually it is in K epsilon model. Just we're using it and we're going to define it. What is the constant, how we can calculate it. For example, if I have a rough mesh texture, CS will be between 0.5 to 1. Okay. To continue in this one, how to calculate the roughness. Roughness Km, or K, which is the height of the roughness, it is constant for any material. You can find this table in BSEN 1991 for 2005 E in table 7.13. Okay. I need to know C, which is, we discuss it here, CS, which is C. Okay. C also in the figure, it can be calculated by using this one or this one. This one in a low Reynolds number, and this one in a higher Reynolds number. Of course, you can return back to the school standard. It is approximately the same, which is how much your Reynolds number you will cross. You will tell me, okay, what is K over B? K already discussed it. This one, roughness height. Don't mess it with this K. It's not this K. Okay. Over B. B is the hydraulic diameter. For example, if you are in the pipes and etc. Something like this. Okay. You will get K over B. You will cut it. You check there. It is 0.4, 0.5, etc. Okay. Of course, if you are in what we name it, if you are doing it like in pipes, especially in pipes, you can refer to Moody chart. Moody chart is the same, by the way, but K, it is written in Moody chart with epsilon, and B is written in D, and C is a fraction factor. Okay, if you don't remember Moody chart, Moody chart. Okay. Okay. This is epsilon over d, and d is the diameter of the pipe, which is etc. And this is the roughness height, and this is laminar area, and this is transient area, and this is fully turbulent. You can cut and check. Okay. Okay. Now I'm going to return back to boundary condition. In the CFD in boundary condition, the major or the main boundary condition you can define for any surface as a velocity inlet, as a pressure outlet, as an outflow. Okay. And of course there is a porous media, and there is other like fan, vent, etc. It's not major, but we're going to discuss it later in the application itself. But here there is a fundamental point, not in the application itself, but in fundamental as theory, as a fundamental. If you're using a velocity inlet model, which is you are boundary layer, which is you defining what is the velocity of the inlet. If you are keeping the velocity is constant, you need to consider that your flow is incompressible. Yes, you can use it as an outflow velocity, no problem, but don't consider any scalar input, because whatever you're going to put it is, there's no benefit for it. Okay. And if you're defining any velocities, you need to check the continuity, return back to the session of the continuity. Okay. Otherwise, it will not imbalance, small imbalance, especially not in transient mode, in the long term mode, or in the normal mode. It will have either very high vacuum or very high pressure. Okay. Pressure outlet. Pressure outlet, it is a back, or it is for a backflow. If you have a pressure, it can work as a backflow. So it can be a pressure vent, pressure release, or a backflow, which is mean pressure is less, the pressure will back in. Okay. You are defining a static pressure. But just note, this define what you study, what you define as static pressure, it is applicable for subsonic. Okay, in supersonic you will use this static pressure, but it will be extrapolated for a new one by the CFD algorithm for a new one in relation to your PS. Okay, so it will not find the same, you will find it different. One of the idea, one extra point, if there is very high velocities in imbalance regarding inflow and outflow, and you find the pressure, it is not releasing or backflowing in not your pressure, that means there is a velocity indication. You have some supersonic issues. Okay. Outflow, don't use it unless you already need it or you need it. Why? If you use it, that means you don't know the velocity or the pressure, because this is the mail you're going to use. Okay. If you don't know both, so you will define the outflow as a mass. Okay. And if there is a pressure outlet, don't use pressure inlet. Okay. So if you have a outflow, and in the same outflow, in the same environment, or in the same universe, or whatever model, you have a pressure inlet, don't use pressure outlet. It will divert. And in the same case, if you have a pressure outlet, don't use a pressure inlet if you need to use an outflow. Okay. Of course, outflow can work in both sides. Okay. Okay. Also, it is for incompressible only. If it is compressible flow, forget it, because you're defining based on mass and pressure is changing. Forget it. Okay. Don't use it for unsteady flow. If you have an unsteady flow, don't use it, because unsteady flow, we know that it is going to change rapidly the pressure, etc., and the velocities, which is you cannot define it. Okay. If the viscosity is varies, not due to incompressibility, for example, if it is compressible, viscosity, so intensity will be varies, but maybe the intensity is varies due to temperatures. So if you have non-constant, you define a non-constant density, don't use outflow. Don't use it in multiphase. It cannot work. Okay, or it will give you non-logic answers. Okay, we'll discuss this. Now in porous material. Porous material, if you have a plate or like this, and or not a plate, like a fabric, and you need to see what is the flow going out on the fabric. You cannot simulate the fabric, okay? But there is a correlation and method to simulate it in an accuracy mode, okay? First, we need to understand the momentum equation for it. Momentum equation, it is mu, which is the viscosity, by over permeability multiplied by superficial velocity. We're going to discuss what is superficial velocity plus C2 1 over 2 rho V also superficial velocity. For superficial velocity, it is a factor multiplied by the correct velocity. This velocity, which is indicate is the let's say this is the actual velocity. This is a coefficient, by the way. This is a coefficient which is a volumetric fraction, which is how much volume of free volume over the total, which is from 0 to 1. So this velocity is less than this velocity, okay? And it is by default, if you have a stream of air which is coming inside a perforated, let's say, fabric, the velocity will not be the same in the fabric. This is the point, okay? Okay. Okay, why we need all of this? We need just to define the pressure drop. Pressure drop, it is a momentum multiplied by the thickness, delta n. In some textbooks, this is delta m. Both is the same. This is the correlations you can use, by the way. C2, which is this part, rho delta n, without the velocity effect, it is this number. And mu over permeability of delta U, it is this number. C2, it is almost this one. Over permeability is this number, but of course it is, you need to check it with the fabric itself, okay? And you can use this correlation for fast forward, okay? طيب, perforated plate, it is the same like a fabric, which is porous material, but it is very thin. So when it is very thin, delta N or delta N, we're neglecting it, okay? So in perforated plate, if we have this arrangement, there is if it is a fraction of open area to total area, and it is almost same like this one, but this is volumes, okay? But with the thickness neglecting, so it is F. Okay, so if it can be, it is just a very fast, you can do it in AutoCAD and calculate it, but it is fast equations. If you have this arrangement, this arrangement is this one, okay? Okay, then we calculate K. K, it is a coefficient of what is the pressure loss, okay? K is equivalent to C2, okay? C2 is K. Some textbooks write C2, some textbooks write K. In both is the same, okay? This is a correlation to calculate K, okay? It is a function of F, by the way, only. And in case of no thickness, delta B is K 1 over 2 rho velocity squared. And in general case, of course, we know that you can use the same equation above. In general case, if you have a thickness for the perforated plate itself, if you want, okay? To write with the thickness of the perforated plate, if you want, okay? Now we're going to discuss the last 2 or 3 items. There is something named the base theory. While you're doing any calculation or anything, you need to, or when you have any information input coming from you, that is the test is like this, or check something and you get some result. It is validating your result. So sometimes you will have an input from a client telling you, oh, we done tests based on your requirement for measurement some of the points which is you don't want to calculate it or you don't want to simulate it. For example, anything, okay? And we found that it is red or it is blue or whatever, any property. So you will ask your client, did you use a measurement tools? He will tell you, yes, I use the device, etc. Then you will tell him what is the accuracy of this device. I'm telling about the accuracy, which is mean give a false number. a false number, not the accuracy how much millimeter up or down. No, give a false number, which is it supersonic or no? Is it something like this? So it is named a base series. Base series is very simple. It is the accuracy of this is the how much percentage what he's saying is correct is equal to the accuracy of the device which is using it to give you a correct result. For example, in 10 tests, he can give you 9 result correct and 1 result false result, which is mean it is incorrect due to the accuracy. Okay. And pH, it is a probability of that defection. In general, this defect, in general, in nature, what is its probability? Of course, this one minus this probability, one is minus this probability, you will get the actual one. You will be surprised if you start to put some numbers. Impact force and energy. Impact force of energy, very quick. If you have a car, or you have just a fundamental, we're not going, this is not CFD by the way, but fundamental. If the car hits the wall, either the time of the impact, 2mv square of the time of the impact, or it is mv square, there's no square, sorry, mv square over 2s, 2s is the compression. It is by the way, and it is very easy by the way, because this one, it is the length over v square of length over time. This will go, time will give, so it will be the same. Okay, okay, but this is a fundamental which we need to know, the force of the impact. Why? Especially like for waterfalls, waterfall for impacts and something which you need to simulate sometimes. It is based on kinetic energy equals the potential energy. Potential energy when water start to fall down, rho gh equal to half rho v square. V, it is equal to 2gh, which is the height of the waterfall, and the pressure at the impact, it is equal to the force here on the area. Take care, area is not constant. Why? Because the flow rate is constant. So, and the velocity getting increasing with height when water start to fall. So if this 2 is constant, so it is constant, and this one get higher while it is fall more and more, so area will be less. That's why the waterfall start to go like this. Then you can calculate, of course, by knowing the q and you know the height, you can calculate the velocity, height, you can calculate the velocity while you calculate the velocity, etc, etc, etc. Okay. You can calculate the area from the area. So the pressure of the impact, it is equal to the force over the area, and the pressure of the impact, it is how much you kept some water. This is from the simulation is, by the way. This is from the simulation. You will check how much is the depth of the simulation and etc. whatever. Okay. Okay. طب how to calculate Q for the waterfall? Waterfall, it is dq equal velocity b في dh, area في velocity. Okay, because the q is different, because the height is different. So what is the velocity is different. So what is the velocity? Velocity is 2gh under root multiplied by b dh, make integration. Voila, it will be 2 over 3 b is the width, 2gh under the root, 2gh under the root multiplied by so h 2g under the root multiplied by g so by h 3 over 2, and h is water film thickness. This, and it is constant. That's it. Okay.